Alrighty, thank you ladies and gentlemen for joining us today for our web training or webinar on understanding the importance of reverse osmosis. Quickly want to go over some housekeeping issues. You can, obviously, you hear me now, access the teleconference through either your PC speakers or you can call in. We will have a Q&A section at the end of the presentation, so go ahead. During the presentation, as you have a question while our guest speaker is speaking, just type them in the Q&A section or the chat window. And like I said, we'll go through those. If we don't have a chance to get to all of them, we'll follow up with you directly if need be through phone call or email. Quickly, I just wanted to introduce myself. My name is Sherilyn Marlowe. I work here at Yokogawa with our liquid analytical products, and I just wanted to briefly, no more than a couple minutes, presentation on what Yokogawa is, just in case, or who we are, in case you're not familiar with us. As a company, our philosophy is to contribute to society through a broad ranging of activities in areas of measurement, control, and information. And individually, we aim to combine good citizenship with the courage to innovate. We were founded in 1915 in Japan, and we came to the North America marketplace in 1957. We currently operate in 33 different countries with 85 different sales offices and companies within those 33 countries. In North America alone, we have 4 headquarters. We have an office in Calgary, Canada, one here in Noonan, Georgia, just outside of Atlanta, one in Texas, and one in Mexico City itself. Outside of these main headquarters, this is just the U.S. We have offices all over the U.S. for support of people right in your backyard. For what industries and products that we offer, we have anything from control and safety systems that you'll use in your control room to your field instruments, your pressure, your temperature transmitters that you see, to your data acquisition, your controllers, your recorders, your signal conditioners, your gas analytical measurements that you guys may have in your process, your liquid analytical, your pH, your connectivity. We also have a system integration group called Measurementation, and they do anything from SEN systems to actual sample panels, water analysis panels, complete shelters. We also have a semiconductor division, a test and measurement division, a meters division for calibrators, handheld communicators, and a life science division. So that just gives you a basic overview of Yokogawa, and I want to thank you for joining us today. And without further ado, I want to introduce our guest speaker today. His name is Mr. David Paul. He is the president of David H. Paul, which is a high-tech water and treatment training and consulting firm located in the U.S. David has over 37 years of experience in membrane and high-purity water treatment and over 26 years of training and consulting in these same areas. He has trained and consulted at hundreds of plants around the world. He has published over 160 technical articles and papers. He currently holds a BS degree in biology and a master's degree in microbiology. So without further ado, I would like to hand the presentation over to Mr. David H. Paul, and we will go ahead and get this presentation started. Give me a moment as it comes up.
Hi, everybody. I think you can see my screen now. It takes just a second to do the transfer. So we're going to talk today about reverse osmosis, and specifically at the end we're going to focus on monitoring and trending performance. Just in case you don't know about David H. Paul, Inc., you can read this as we scroll down. We have just a ton of training programs basically in all aspects of high purity water. So we have online, classroom, hands-on, I mean lots and lots of days of a training program. And we also do consulting. So if you're interested in learning more about our services, you can go to www.dhptraining.com. Okay, well, with Yokogawa, we are doing a 4-webinar series, basically on high purity water, but we're taking it section by section. So 2 weeks ago, we had a high purity water treatment overview, and in that overview, we looked at how in today's high purity water treatment systems, almost always you have reverse osmosis as one of the treatment steps. That's the big gun. That is the bulk total dissolved solids removal piece of equipment or technology. And the equipment in front of the RO unit is called pre-treatment. It's there to protect the RO unit. We're going to talk about that in a couple of weeks. And then the permeate coming out of the RO unit, since it rarely meets end-use specifications, we usually have to polish it. So that's called post-treatment. And we're going to discuss that 4 weeks from today. So we started out 2 weeks ago with the overview. Today, we're going to talk about RO units, again, emphasis on monitoring and trending. And then 2 weeks from now, we'll be doing the same thing with pre-treatment. And then 4 weeks from today, we're going to be looking at monitoring the post-treatment or the high purity water. So it's going to be the same time and day of the week each time, just 2 weeks apart. So today, we're looking at reverse osmosis. So this agenda that you see, we have 1 day, 2 day, and 3 day seminars that cover basically this exact same agenda. So in 1 hour, we're not going to be able to go into a lot of detail, but you'll get the high points and understand when we get to the monitoring and trending. So just a quick introduction. Everything I'm going to say is going to be true for the smallest RO units or the largest RO units. Reverse osmosis is reverse osmosis. And whether we're talking freshwater, brackish water, or seawater, the principles are the same. Now, the pressures are going to be different, but the principles of operation are going to be the same. So here is a particle size scale, and this isn't precise, so you're not going to see this in a chemistry course. But I think it's valuable in today's water treatment to think of 1/100th of a micron, and a human hair is about 100 microns. So 1/100th of a micron, very small. Things that are larger than that are particles. So we see here some examples. Virus, we know that's a very small particle. Even if we chop the virus up into 100 little pieces, our most powerful microscopes would still see a little piece of something, and we would call that a particle. You'll hear them called suspended particles. But just think of it as a particle. If they're smaller than that, then they're dissolved. Well, we have conventional water treatment that's been developed, over the last 100 years or so to remove the bigger particles. But in today's world, if we want to remove particles greater than around 1/100th of a micron, we're almost always going to use membrane technology. We're going to make a membrane that has holes or pores through it of 0.1, 0.2 micron. We call that membrane technology microfiltration. If we want to remove essentially all particles, then we'll have a membrane that has pores through it in the 0.01, maybe to 0.05 micron range. We're going to call those ultrafilters, and that's an ultrafiltration technology. But when we want to remove dissolved substances, we are now in reverse osmosis. Reverse osmosis comes in 2 flavors: nanofiltration, which is a looser RO membrane, and then hyperfiltration, which is the tightest membrane. You don't hear the word hyperfiltration very often. You usually hear MF for microfiltration, UF for ultrafiltration, NF for nanofiltration, and RO for hyperfiltration. But just to remember that nanofiltration removes dissolved substances, therefore it is a reverse osmosis membrane. These membranes are semi-permeable. They're permeable to water molecules. In other words, water molecules can pass through in either direction readily. Not very permeable to much else. So suspended particles, if the membrane was perfect, then no suspended particles would go through. And if the O-rings were perfect. Dissolved substances, though, do pass through, the little red balls there are dissolved substances, but they pass through slowly. So that's different. This isn't like a filter that we're used to, where if the contaminant is larger than the pore size, it will never go through. Well, that's not the case with RO. The dissolved substances can go through by diffusion, which is random motion, but they don't go through very quickly. This is a very important slide, and like I said, in a regular course, we would spend an hour or two getting up to this point. But RO membranes really are extraordinary. So we can divide contaminants into dissolved contaminants and suspended contaminants, so particles and dissolved. We can subdivide dissolved into charged, meaning they have a positive or negative charge, or uncharged, neutral. And we can subdivide suspended into living and non-living. The charged contaminants, and this is going to be most of what we deal with in water treatment: calcium, magnesium, potassium, bicarbonate, sulfate, chloride. All these things that have positive and negative charges are very, very well rejected by RO membrane. And the more charges a substance has, and we call these ions. If they're charged, we call them ions, or we call them ionic. Well, the more charges, the better the rejection. So we see here, and this is just an example, a certain membrane. Each membrane is a little different. But if we had a membrane that rejects 99% of single chargers, then for the double chargers it would be higher, and the triple chargers would be higher. Uncharged things, though, have to be rejected based upon size. That's why water molecules go through. Water is uncharged, even though it's polar. For those of you who know what polar means, it's polar, but it's uncharged. It does not have a +1 or 2 or a -1 or 2 charge. It's neutral. And it has a small molecular weight, has a molecular weight of 16. So anything with a molecular weight of 16 or smaller and is uncharged is going through that membrane. Well, the gases, oxygen, nitrogen, CO2, hydrogen, sulfide, all of the gases dissolved in water go through the membrane. There's little, if any, rejection of dissolved gases. Other things like uncharged organics, uncharged silica, they have to be rejected based upon size, and this MW is molecular weight. So we infer or approximate the size from its molecular weight. So well, we know that water is molecular weight of 16, so we'll just round it off. These are just approximations that I'm showing you here. 0 to 20, we'll say 0. There's going to be no rejection. By the time you get to 50 molecular weight, maybe we're up to 40, 50, 60% rejection. By the time we get to 100 molecular weight, we're probably in the 90% rejections. And by the time we get to 200 molecular weight, now we're into very high rejections. So the larger the uncharged substance, the better the rejection. And a perfect membrane, if it's able to reject dissolved substances, if it was a perfect membrane, it would be 100%, but nothing's perfect, so you'll get a few suspended particles that go through the tiniest ones, but it's nearly 100%. Okay, so now let's move on to the next topic, osmosis and reverse osmosis. So osmosis is the tendency of water to pass through a semi-permeable membrane into a solution of higher TDS. So in this picture here, the rectangle is an RO unit. And it could be the smallest RO unit in the world to the largest RO unit in the world. But the rectangle is the RO unit. The diagonal line here is all of the membrane, all of the semi-permeable membrane or RO membrane that is in that RO unit. Well, when your high pressure pump is off, if you have feed water on one side and you have permeate on the other side of the membrane, osmosis will occur, because osmosis is the tendency of water to pass through a semi-permeable membrane from lower TDS to higher TDS. So for those of you that deal with seawater RO units, especially that have been around a long time, you'd have a suck back tank. So when you shut down your RO unit, there was enough permeate to suck back to provide the water for osmosis. You don't see that as much today, but that was very common long time ago. So to reverse osmosis, we have to get water to go in the opposite direction, to go from the feed side to the permeate side. Well, to get feed water to go from the feed side to the permeate side, we have to overcome the back pressures. There are two back pressures that we have to deal with. The osmotic back pressure, and that's really the force of osmosis. And that's a function of the dissolved solids content on the feed water side of the membrane. So in American units, you just divide this by 100, which move the decimal place over 2, gives you a ballpark osmotic back pressure. It's not exact, but it's a ballpark. To get in metric units, you divide the milligrams per liter by 1,500, and that gives you an approximate bar pressure, osmotic back pressure. Okay, so we have to overcome the osmotic back pressure, and we have to overcome the permeate back pressure. Now, if this permeate is going right to an underground tank, there would be very little back pressure. If this permeate is going into a 30-foot or 10-meter high tank, then we're probably looking at close to 15 psi or 1 bar of back pressure. So we have to overcome these back pressures in order to reverse osmosis. So in this case, we have 25 psi or 1.7 bar of back pressure. So we are going to take a high pressure pump. Whoops, sorry, I went the wrong way. Take a high pressure pump, pre-treat the water, pressurize it, and we're going to give it enough pressure where we can overcome the back pressures and we can reverse the direction of osmosis, and that's what we call reverse osmosis. Net driving pressure is what forces water through the membrane, and that's simply the feed pressure minus the two back pressures, the osmotic back pressure and the permeate back pressure. So again, in a longer course, we would spend 30 minutes to an hour and have you play with calculating net driving pressure. For this, what I want you to see is this is the way RO units work. You take a pre-treated feed water, you pressurize it in a high pressure pump, and you send it into an RO unit. Due to the net driving pressure that you have, you're going to force a lot of water molecules through that membrane. The dissolved substances can't go through the membrane very readily, so they're going to be concentrated. So every inch or centimeter of the way from the feed to the concentrate, and concentrate is also called brine or reject. So whatever you want to call it is fine. I've got concentrate here. All right, so the total dissolved solids, the TDS, the dissolved substances are concentrated every inch or centimeter of the way. But they're all diffusion. They're all moving randomly. And due to that random motion, there's going to be a certain amount of diffusion. Well, you have more concentration in the last inch or centimeter than you have in the first. So you have more diffusion in the rear of the RO unit than you have in the front. That means that you're going to make better quality permeate at the front and worse quality permeate in the rear. Okay, so putting those two together, the way RO units work is you take this pre-treated feed water, you go to a high pressure pump, you give a net driving pressure that will force a lot of water molecules through. Every given moment, there's a little bit of diffusion which is diluted by a whole lot of water molecules. So that's how we can go from seawater up to, over 40,000 milligrams per liter to drinking water of less than 300, 500 milligrams per liter. So excellent technology. One other thing to know about the membranes is that temperature is a huge impact on your pressure requirement. So as the water is warmer, the water is less viscous. So you can think of it as thinner. It's not as thick. So the warmer the temperature, the lower the viscosity, The lower the viscosity, the lower the net driving pressure required to produce the same amount of permeate. So if you're in a place where in the summertime your feed water is warmer, the wintertime it's colder, then it means that in the summertime you'll have to apply the least amount of pressure, and in the wintertime you'll have to supply the most amount of pressure to make the same amount of permeate. The other impact of temperature is its impact on diffusion. So as the temperature is warmer, dissolved substances can diffuse through the membrane easier. So in the summertime, you'll make your lowest quality permeate. In the wintertime, you'd make your highest quality permeate. Okay, so that's talking about the membrane. Now the membrane is put into a piece of equipment called a membrane element. And again, we'd spend an hour or two. In our seminars, we actually have you make simulated RO elements so that you know exactly how they work. We're just going to look at them here. We're seeing from 4 different manufacturers. These elements basically work the same, and they're basically interchangeable. We're going to put these elements, these membrane elements, into pressure vessels. Here's a small pressure vessel, here a larger pressure vessels. Here's a picture of elements that are going into pressure vessels. So the membrane elements go into pressure vessels. The pressure vessels in parallel and in series then make up the RO units. So if the high pressure pump is only feeding one set of parallel pressure vessels, each pressure vessel is producing permeate, that's the water that goes to the membrane. And each pressure vessel produces brine, reject, or concentrate. If the feed water just goes to one set of parallel pressure vessels and the concentrate then goes to drain or whatever, that's called a one-stage system. 99.99% of all seawater RO units are going to be one stage, because a stage will give you roughly 50% recovery, excuse me, 50% of the feed water will go through the membrane, and seawater RO units on real seawater, not bay water that may be dilute, but real seawater, will be less than 50% recovery. In industrial applications, the most common is 75% recovery. So in this case, we're going to take the concentrate from the first stage and we're going to send it to a smaller number of pressure vessels. That's called the second stage. So when you're getting into the 75, 80% recovery types of RO units, you'll typically see a 2-stage. If you go to higher recovery, so you're 85, 90% recovery, then it's not uncommon to see 3 stages. Okay, so we've talked about how RO systems are put together and basically how they work. But there are 3 problems that we have to treat our way and operate, monitor, maintain our way out of. These problems are scaling, fouling, and chemical attack. So you won't see this, our definitions everywhere. So this is not a universally accepted definition, but this is our definition. You'll sometimes read an article that will talk about calcium carbonate fouling. We would never say calcium carbonate fouling. For us, it would always be calcium carbonate scaling. We want to distinguish between scaling and fouling. So for us, scaling is caused by dissolved things in the feed water that precipitate out in the RO unit due to concentration. So as you concentrate dissolved substances, at some point they get as close together. When I say they, I'm talking about calcium +2, carbonate -2, calcium +2, sulfate -2. You get these mainly double charged positive and negative ions close enough together that at a certain point they're as close as they can be, where they're attracted to each other as much as they are to anything else in the water. So at that point we call it 100% saturation. You can't get any more of the calcium and carbonate, for example, to dissolve. So if you go above 100% saturation, then you're going to force a portion of the calcium and carbonates to come out of solution, turning into a solid. We call that scaling. So here's a picture of some scaling on the outside of a membrane element and also scaling on a membrane element. And then, so this is the surface of the membrane that you're seeing between these crystals. The crystals here are actually in the feed stream. So there's a feed spacer that goes on top of this. The feed spacer has been removed, so you're just seeing the calcium carbonate crystals on top of the membrane. Scaling is due to concentration. So if anywhere in this RO unit, from the first inch or centimeter to the last, if anywhere you reach 100% saturation or you exceed the capability of your scale inhibitor, anti-scalant, to control the scaling, then from that point on, you're going to scale. So scaling is a function of concentration. So based on that, which element would most likely scale in this RO unit? You have a two-stage RO unit, you have 1 through 12 elements. Well, if you guess number 12, you'd be right, because it's due to concentration. So it's not uncommon when you scale an RO unit that number 7, 8, 9 even may not be scaled, but maybe 10, 11, 12 are scaled, or maybe 11, 12 are scaled. It just depends on when you've either exceeded 100% saturation or you've exceeded the limitations of your scale inhibitor to control the scaling. All right, that's scaling. Let's talk about fouling. So for us, fouling is either due to particles. They could be living or non-living. Could be bacteria, which are living. Could be dead bacteria, non-living. Or it could be silica particles, silt, clay, rust, iron. You know, any particulate material that comes into the RO unit and stays would be fouling. And also sticky polymeric material. So it could even be polymers, any kind of substance that would come in and plug up the feed channel. We would call that fouling as well. So here's a picture of an unrolled membrane element on the left, and then on the right is the feed spacer. The feed spacer would actually be laying on top of the membrane. There's always a feed spacer in contact with the sheets of membrane. We can see this should be perfectly white. This is the foulant, but we also, this is the first element, and this is the feed going from right to left. And we can see there's more foulant in the first half of this element than in the second half, and that's very common. We'll see why here in just a minute. And here we also see that the foulant is plugging up the feed spacer. Just a couple of points. Fouling, your fouling rate is really going to be a function of water flux and cross flow. The water flux is how much water you put through a given area of membrane in a given amount of time. So in American units, we're going to call it GFD, gallons per square foot of membrane per day. In metric, we're going to call it LMH, liters of permeate per square meter of membrane per hour. So we're going to see here that the water flux rate changes every inch or centimeter of the way. So if we just look in the membrane element inside the pressure vessel, we see 4.67 gallons per minute, or 1.06 cubic meters per hour, is being produced by the first membrane element. It's even more dramatic than that, because actually the first inch or centimeter is going to make more water than this, because this is an average. So the first inch or centimeter makes more permeate than does the last inch or centimeter, because the net driving pressure is higher in the first inch or centimeter. But as we go along here, we see that the amount of permeate being produced drops. So every element makes less permeate. So that means the water flux is the highest in the first inch or centimeter, and it's the lowest in the last inch or centimeter. Cross flow is the feed concentrate flow rate. So if the feed is coming in here, the part of the feed water that doesn't go through the membrane, that actually exits in the brine reject or concentrate stream, this is the cross flow. This is the flow rate that's keeping the surface of the membrane cleaner. It's a tangential flow, so think of it as a scouring or a cleaning flow rate. So right at the surface of the membrane, you have what's called the boundary layer. And this boundary layer, depending on the feed concentrate flow rate, the boundary layer can be taller, in which case more particles can lay out on the surface of the membrane, or at a higher cross flow rate, which means a higher feed concentrate flow rate, the boundary layer is smaller, so you have less fouling. So again, the water flux rate and the cross flow rate determine your fouling rate. All right, so based on what we've just covered, which element 1 through 12 would be the highest fouling rate? In other words, has the highest water flux rate. So if you guess number 1, then you got that right, because the number 1 is always going to be your highest fouling rate because it has the highest water flux rate. And water flux is more important than cross flow to determine your fouling rate. Then the last problem we'll talk about is chemical attack. The chemical attack is usually by oxidation, not always, but usually, and that's usually chlorine. So you actually can't see it. I mean, if you do an autopsy, you open up the element, you can't see chemical attack. But we'll use dyes on the feed side of the membrane. Now here we see the dye is very dark on the feed side because there's bio and other things that are absorbing the dye. But when we turn it over to the other side, we don't want to see any dye going through the salt rejecting layer of the membrane. Whereas in this case, here's the feed side, and in autopsies we do this. This is the in the front of the element is the feed side of the element, the middle of the element, and the concentrate end of the element. When we turn this over and you see this kind of pattern, then we're seeing that there's membrane damage. We've got chemical attack. So we want to be able to find these problems out early. We want to catch them while they're hopefully in a reversible stage, and it costs us the least amount of money to fix them. So we're going to have to monitor things that you have to basically monitor in any water treatment plant. So really not that unique to reverse osmosis, except for silt density index, and we're going to talk about that 2 weeks from now. So why do we want to do this monitoring? Again, to make sure we're operating as designed and we catch problems at an early stage. So here are for a 2-stage unit, here are the 9 instruments that you absolutely have to have. These are not nice things to have. These are absolutely necessary. So if your RO units don't have these 9, then you need to change that. So temperature doesn't have to be right on the RO skid, but we have to have temperature somewhere on the feed water line, because we've already seen that temperature is a huge impact on the pressure requirement to make a certain amount of permeate. So we want also the pressure of the feed, the pressure between the stages, that's the interstage, pressure between the stages, and the pressure of the brine rejector concentrate. We want that interstage pressure so we can see if the problem is in the first stage. So if we see a higher pressure drop in the first stage, we're going to think fouling. Whereas if we see higher pressure drop in the second stage, we're going to think scaling. Then to monitor the performance of the membrane, how well it's able to reject substances, then we want a conductivity meter on the feed, and we want a conductivity meter on the permeate, so we can see how well the membrane is able to reject feed water conductivity. And then, of course, we have to know the flows, the flow of the permeate and the flow of the concentrate. And because of the net driving pressure calculation, we also need to know the permeate back pressure. So these are the 9 instruments that you absolutely have to have on any 2-stage RO unit. On a 1-stage RO unit, you wouldn't have the interstage pressure, so you would only need the other 8. All right, so this is just for your reference. So when you're looking at the slide, because you will receive a PDF of this presentation after this webinar is concluded. So this is just for your reference so that you can see on that diagram on the slide before what each one of those means. And I just threw in a couple of pictures of, you know, on some units, everything's going to be manual. You have manually controlled valves, open and closed valves. You just have pressure indicators, pressure gauges like this. Here we're looking at feed, interstage, and concentrate feed pressures for 1 RO unit. Or for more expensive systems, then everything may be automated. You may have indicating transmitters everywhere. So if you go out to the actual RO skid, you can look and see what the pressure is here, but it's also sending signals to the HMI, the PLC, and it may be controlling, it may be a pressure indicating controller as well. So again, for your reference, the other instruments that you need, and just showing a couple of instruments. In this case, I'm just looking at indicating transmitters for conductivity and flow. And if you're injecting acid, then you have to have pH. Not very many systems inject acid. Most just inject antiscalin or scale inhibitor for scale control. Also, if there's chlorine in the feed water and you're dechlorinating, then it's common to have an oxidation reduction potentiometer, ORP, or you may have an on-stream free or total chlorine analyzer, or at some plants you're just taking these manually, taking manual readings on a periodic basis. So again, just a picture of an on-stream pH indicating transmitter. Okay, then the last section is not only is it important to monitor, but we need to trend this because nobody's going to remember what happened 6 months ago, 2 years ago. So we want to take the daily readings, but we want them trended. And I find this is a weakness that a lot of plants. Everybody takes the data. I mean, there's virtually no plants that don't have somebody going around and putting on a log sheet that, okay, this is what the pressure is, this is what the temperature is. They're walking around and they're doing the daily monitoring. But it's absolutely critical that you trend at least 3 things. Normalized permeate flow probably is the most important. I'll just mention the normalized permeate flow. We won't get into the equation. It's not complicated, but it would just take too long. We can't get it done in a 1-hour webinar. But normalized permeate flow normalizes to the pressure, the net driving pressure that you had at startup, and the temperature that you had at startup. And then the normalization equation takes a look at the temperature you have today and the net driving pressure you have today. And if on your graph it's flat, it's the same as it was at startup, then it means don't worry. As long as the graph is flat, you don't really care whether the pressure goes up because it's telling you that it's going up for some good reason, like the TDS of the feed water went up, the temperature of the feed water went down. So So you want to monitor normalized permeate flow and normalized or not pressure drop. You want to do pressure drop across the first stage and second stage and trend that. Some of the membrane manufacturers' software normalize it, most do not. Most, you have to do your own monitoring of first stage, second stage pressure drops. And then normalize salt passage. So just to wrap it up, and then we'll go to Q&A. Scaling, when you have normalized permeate flow drops, that means it's taking more pressure today than it took at startup. So you've got something on the membrane, in the feed spacer, or both. You've got something that's causing you to have to supply too much pressure, and it's not due to something okay, like the temperature's colder, because that's accounted for in the normalization. So scaling or fouling will cause the normalized permeate flow to drop, but when you're looking at pressure drops, scaling is going to be a second stage problem, not a first stage. So in this case, by seeing the normalized permeate flow is dropping and the second stage pressure drop is going up, that would be symptomatic of scaling, and the salt passage goes up with scaling. For fouling, again, normalized permeate flow is going to drop, meaning you're having to supply more pressure than you would if the system was clean. But now fouling is mainly and certainly most of the time a first stage phenomenon, especially at first. So salt passage for fouling, sometimes the salt passage will increase, but especially for bio, for organics, it may actually even go down a little bit, but you don't see a dramatic increase in salt passage. Chemical attack, you can think of it as holes in the membrane. So now it takes less pressure to force the same amount of permeate through the membrane. So we see that the normalized permeate flow goes up. Chemical attack does not change the resistance of flow in the feed channel, so you don't see a change in pressure drop, but you certainly see a change in salt passage. All right, so what we've covered in this webinar is we looked at basically just a little highlight of the various theories, the various pieces of equipment that go into an RO unit, so we can understand how an RO unit works. And then we looked at the scaling, fouling, chemical tech problems, and then the daily monitoring requirements and the weekly trending requirements. So I thank you so much for your attention, and we'll now, Ms. Sherlyn will take over and she'll ask the question, and then there'll be just a brief pause, and then I'll give the answer.
All right, thank you very much, David. Just want to put up the slide real quick so you guys have our contact information. Go ahead and start typing in your Q&As into the question and answer section. We already have a couple that are that have started to come in. Give me one moment here. All right, the first question, David, that came in was, where'd it go? There it is. Do you know if ORP can alone be used to determine the proper sodium bisulfite feed?
Yes. There can be a feedback from your on-stream ORP meter to a sulfite injection system. The challenge with ORP is that different temperatures, different TDS, different waters will have a different zero as far as chlorine residual. So that's the thing that you have to learn for your plant, is you're going to have to find, what millivolt reading. So I was talking to a plant this morning that is 240 millivolts is their alarm set point. There's other ones that'll be 180, other ones that'll be different. So, but absolutely you can do that. You can have a feedback loop and it can inject your sodium sulfite. But remember that the ORP meter is in the dechlorinated stream, which means that bio is likely to grow. So that is an instrument that you should have on a periodic preventive maintenance, pulling it out so you can clean the bulb, because the biofilm may develop on the bulb and start messing up your readings.
Alrighty, thank you. The next question is, what is the optimum water temperature for RO?
It depends totally on what you want to look at. So if you wanted to look at what temperature of water would I get the best quality permeate? Well, the answer would be 33 degrees Fahrenheit, just before freezing. But that would also cost you a tremendous amount in energy. It really is, it's pretty phenomenal that every 1.8 degree Fahrenheit, 1 degree C, is going to require a 3% change in net driving pressure. So it's quite significant. So if you were looking instead at pressure, strictly electricity, all right, then you'd want 45 degrees C, 113 Fahrenheit, because that would be the top temperature, so you'd need the least amount of pressure to force the same amount of permeate through the membrane. But now you'd have to have hot water, you'd have more diffusion, so the quality of your permeate would be less. So there's no specific, but I'd say if you're looking at biofouling, then less than 50 degrees would be best. But most RO units are either at ambient temperature and they don't do any changes, or a lot of times if it's in a place that has cold water in the wintertime and there's any waste heat available, there might be a heat exchanger ahead of the RO unit. And most of the time when you see that, you see that they're controlling it in the 70 to 75 degree Fahrenheit range.
Okay, thank you. We have a couple of different questions about pressure, so I'm going to try and ask all these, one after the other. The first one is, going back to your pressure values, you had a combined back pressure of 16 psi and a driving pressure of 200 psi. The particular individual didn't understand the need for the large difference. Can you please explain?
Well, the net driving pressure is what forces water through the membrane. So if you double the net driving pressure, you'll double the amount of permeate that's produced. So you need that amount of forward pressure. So in that case, it was 200 psi and you had 25 psi of back pressure to make the amount of permeate that you wanted. Now you can't just decide, okay, well, let's double that to 400 psi, because then your water flux would be too high and you would have fouling and other problems. So there's a range of water flux values that are typical for surface water, another set for well water, another set for wastewater, seawater. So you have a specific water flux range that is appropriate for a given feed water, and then you have to make enough, you have to supply enough net driving pressure within that range that'll give you the amount of permeate that you want.
Going off that same question, someone has asked, is there any pressure rise rate, example like 10 psi per second requirement for that inlet water into the RO plant?
Yes. Most manufacturers will recommend that you do have a slow opening valve, or you have a VFD controlled pump, so that your rate of rise of the flow rate and pressure going into the RO unit is controlled. so that you're not doing a water hammer or you're doing something that would damage the membrane.
Thank you. Do you know what is the most probable problem that is occurring in NPF, NSP, and NPD are all increasing through time?
Are all increasing through time. Okay, so the normalized permeate flow goes up. Out of those three, there's only one that does that, and that is membrane damage, chemical attack, or cut membrane or O-ring leaks. Anything that allows water to go from the feed side to the permeate side easier would make your NPF go up. But if you have NPF going up, then if your pressure drops are also going up, then you have two things going on. So because membrane damage or O-ring leaks by themselves would cause the salt passage to go up and would cause the NPF to go up, but would not make the pressure drop go up. So the only way you could see this if you increased your flow rate. So the pressure drop is a function of temperature and flow rate being the more important. So when I'm saying that the pressure drops don't go up with membrane damage, that is based upon the flow rates are not changing. So you're controlling your feed, permeate, and concentrate flow rates at the same. You're not allowing them to change. But if you had membrane damage and you increase the feed concentrate flow rate, then that could increase the pressure drop as well. But if you kept the flow rates the same, no different than for the pressure drop to go up as well as the normalized permeate flow in salt passes, that would mean you have two problems going on. One would be membrane damage or bypass, and at the same time you've got some sort of foulant or scalant that is causing the increased pressure drop.
Okay. Do you know, or can you explain what SDI means, and is it necessary for well water and surface water?
That's actually going to be covered 2 weeks from now, so I'm just going to give you a really quick answer. Silt density index. You want to do it on well water, but you don't have to do it all the time, because if you have a deep well that doesn't change a lot, you just want to make sure you understand what happens when you turn on a pump. Do you have high SDIs for 1 minute, 2 minutes? But after that, you probably have a pretty good idea of the fouling potential of your well water. Surface water is totally different. Surface water, you want to do SDIs a lot because, you know, if it rains today, then the SDIs will be high tomorrow. But we're going to cover that in a lot of detail in 2 weeks.
I think this question then kind of goes over the same thing you'll probably cover next week, but the question is, comparing to thermal desalination technologies, do you think the salination becomes more feasible? What about the huge municipality drinking water plants?
Absolutely. If you look around the world today, about the only time that you see thermal winning out over RO is when you need a power plant at the same time. So if you're going to build a power plant, and this is mainly in the Middle East, that you're going to build a power plant and you need drinking water, you may see that a significant portion, maybe even all of the water is being produced by thermal. But it's not as common. I mean, certainly if you look over the last 30 years, there have been more of the drinking water plants in the Middle East that are RO than thermal. Now that's not, I'm basing that on numbers, not on cubic meters per hour or gallons per day. or cubic meters per day. The biggest plants in the world, I think the biggest one is going to be thermal.
Okay, now we're getting into some kind of basics of it. There's a couple questions. One is, what is the average conductivity range of the permeate in a one-stage and a two-stage system, as well as what are the typical flows in a municipality treatment plant using RO systems that you've seen?
The conductivity is a function of percent recovery and feed water TDS. So you're talking about diffusion through the membrane. So let's say you had 100 milligrams per liter in the feed side. You know, you may have 1 milligram per liter or 2 milligrams per liter in the permeate. Whereas if you have a seawater with 40,000 milligrams per liter, you may have 200 to 400 milligrams per liter in the permeate. So the conductivity or TDS of the permeate is going to be a function of the dissolved substances on the feed water side of the membrane, which again is a function of the feed TDS and the recovery rate, how many times you're concentrating that water. And then the flow rates are going to vary. I mean, oh my gosh, I don't know what the largest RO unit in the world is, but it's probably somewhere between 4 and 10 million gallons per day for one RO unit. I mean, these big new seawater RO units are just gigantic. And then when you have, and then under the kitchen sink, little RO unit, you've got 5 gallons a day, maybe.
Okay, thank you. We're getting really close to our hour mark, so thank you, ladies and gentlemen. We do have a few more questions, so if you have time and you'd like to stay on while we answer them, please feel free to do so. So got a question here that is how to, I guess it's stated, how to increase the flux by step.
I don't quite understand what you mean by step. But when you increase the water flux, you increase the fouling rate. So it's not necessarily a good thing to increase the water flux. Occasionally when I'm consulting and there's a bad fouling problem, I reduce the water flux, because reducing the water flux will reduce the fouling rate. So I'm sorry, if you could ask the question or type in another question about the step. I'm not sure what you're asking for there.
Not a problem at all. While we're waiting for that question to come in osmosis, what dictates the low concentration solution to permeate to high concentration solution?
It's really quite simple. It's strictly going from high concentration to low concentration. So it's no different than diffusion of dissolved substances. Now, when we talked about diffusion of dissolved substances, then the feed water side has more dissolved substances than the permeate side. So diffusion is going to be from areas of higher concentration to areas of lower concentration. But if you look at the permeate side, the concentration of water molecules is higher in the permeate than it is in the feed. So you have more water molecules in contact with the membrane on the permeate side than you do on the feed side. Therefore, by diffusion, you have more water molecules going from the lower TDS solution to the higher TDS solution. So it really is no magic to it.
Thank you. Couple more here. Going back to NPF, someone wants to know, do you always have to use a temperature correction factor when you calculate your NPF? And if so, where do you get this factor?
Yes, you have to have a temperature correction factor. So you get these from the membrane manufacturers. Some manufacturers manufacturers, you can go to the website and you'll actually see a table, and it'll go from, you know, zero degrees Celsius, 32 degrees Fahrenheit, or maybe it starts at 35 or 40, and then goes up to the maximum, usually a 45C or 113F, and it gives the temperature correction factor. You do have to have that in order to normalize the data.
Thank you. David, if you've got a couple more minutes, we are at our 1 hour mark. We would like to ask you some more questions if you're available.
Yes, that's fine.
You mentioned some normalized equations. Do you know where we can go to look to find these equations?
I don't. I think if you did a Google search for normalized permeate flow equation, that you'd find it. It might even bring up one of our seminars. I'm not sure. I haven't done it, but also if you go on Dow or Hydronautics or Torrey or other membrane manufacturers' sites, and you go to their design software, which is free and downloadable, and then if you go to the normalized permeate flow or normalized salt passage part of the spreadsheet and you click on a cell, then you may either see the equation pop up where you'll get the equation there, or some of them also have a sheet. They have somewhere on their website where they have a document that actually gives you the equations that they use.
Thank you for that. For an ESD shutdown on the plant, is there any mechanism to protect the membrane from damage?
Would you repeat the first? Was it an emergency shutdown? Is that what I heard?
I think so. They shortened it to ESD for an ESD shutdown of the plant. Is there a mechanism to protect the membrane from damage?
I don't know what the ESD stands for, but when you shut down, of course, you don't want a water hammer. You don't want the RO unit to drain, especially if it's going to sit there for a while. As far as for protection, it's as a minimum, you would like a post-shutdown flush with pre-treated permeate that pushes the concentrated water out of the RO unit while it's going to sit there. Even better is to do a post-shutdown flush with permeate, and the best, doesn't happen very often, but high purity water. So in some high purity plants, they even flush the RO unit in deionized water, ultra pure water.
In this particular incident, the ESD was emergency shutdown. Does that change your answer in any way?
No. No.
Okay. We've got 5 more questions, and that is it for the day. So the next one is there specific consideration to be taken when using an RO and reuse of treated sanitary water for producing demineralized water for power generation?
The big challenge there, of course, is fouling of the RO membrane system. But there are lots of applications now. The most common being, if you're going to take a sanitary waste, going through a membrane bioreactor, which is going to be, your regular, activated sludge with the, the regular treatment steps that you would go conventional, but then you have an ultrafilter as your tertiary treatment. So after the bugs have eaten what they're going to eat, the water is actually going to pass through a UF membrane, and that becomes pre-treatment to an RO unit. Still does not mean that you won't have fouling of the RO unit. You may still have to clean on a regular basis in order to control it, but it's common today to do that.
Right. In a seawater application, is ultrafiltration upstream of the RO system necessary?
It isn't necessary, but it's certainly becoming more common. If you have a good either single, a well-designed and operated dual media filter, or even two dual media filters in series, two treatment steps, for certain feed waters, this does a fabulous job. So you don't have to have an ultrafilter, but certainly more and more of the newer RO units are putting in membrane filtration, which would be microfiltration or ultrafiltration in front of the seawater RO.
Two smaller ones here is, do you know what the recommended velocity is on an RO plant? And then as well as, what is the capability of RO units for TOC removal?
So the velocity, I don't have it in feet per second, which what I use is I would like to see 20 gallons per minute per pressure vessel coming out of the RO unit, out of each pressure vessel. So if you have 20 gallons a minute, then you have a good cross flow rate. Up to 25 or more would be outstanding. But there is a price to pay for that, because as you increase the flow rate, you're going to increase the pressure drop, which means you're going to have to increase the pump pressure, which means you're going to pay more in electricity. But as far as fouling is concerned, which is the biggest problem, the thing that I deal with more than anything else, that's what I go by. If I can see 20 gallons a minute to 25 gallons a minute coming out of each pressure vessel, then I'm pretty happy with the cross flow. And the second one, TOC removal, it depends totally on the TOC, because a lot of the TOC is going to be uncharged. So let me give you an example. An organic molecule like methane, that's going to go right through the membrane. You're going to have zero rejection. Ethanol, drinking alcohol, it's uncharged. It has a molecular weight of, I think, about 50, 60, somewhere in that range. And ethanol, because it's small and uncharged, maybe you're only going to get 40, 50, 60% rejection. If you have big organic polymers, if you have tannins, lignins, these are going to be rejected well. So it totally depends on the size of the molecule, how much of the TOC you're going to remove.
Thank you. And the last two, and hopefully we'll get this in just a couple more minutes, is what is a DOHS process?
The DOHS process is a patented process for a company in Israel, and it stands for direct osmosis high salinity. And in this, you're using the power of osmosis to clean the membrane. So you inject a slug of sodium chloride brine into the feed water of an operating RO unit. This slug of salt then passes from the first inch or centimeter to the last. Because of the osmotic pressure, even though your high pressure pump is still going and you're making permeate downstream of the salt plug and later upstream of the salt plug, right at the salt plug you go into osmosis, and water molecules are going from the permeate side of the membrane to the feed side of the membrane, helping to lift off foulant that is on the surface of the membrane.
Thank you for that. And our last question for today is, I would like to ask, what is the best dechlorination method that can be used with chlorine-sensitive membranes while avoiding biofouling of the membranes?
Well, we don't have a perfect one. So if you can invent one, it would be a great benefit to all of us. The two common ways would be sulfite injection, and sulfite injection is great. You just have to make sure you mix up the chemicals, or maybe you have a big enough tote that you don't have to mix up chemicals, but need to make sure that your potency in a day tank doesn't drop, and you don't want to overfeed, because if you overfeed sulfite, then not only do you get rid of chlorine, you get rid of oxygen, and then you turn it anaerobic, and you end up with you can end up with anaerobic bacterial fouling. The other way of dechlorination, which works great, is activated carbon, but again, biofouling can be an issue for activated carbon as well. So we don't have a perfect dechlorination system yet, but both of them work well, but you have to control the biofouling.
Thank you, David. Everybody, thank you for joining us today. We ran 10 minutes late because of the questions and answers. I do think that they were good questions and good answers, very informative presentation. You have our contact information here if you would like to get a hold of us. There will be an email, like David said, that goes out within the next 24 hours with a copy of the presentation slides, as well as, since it is coming from Yokogawa, if you would like to get a hold of David and you forgot to write down their contact information, just let us know and we will get you directly in contact with them. So David, thank you for your time. Everybody else, thank you for your time, and we hope to see you again on some of our seminars again. Remember, the next one's in 2 weeks, and it's about pre-treatment. Thank you, and have a great day, everybody.